All right, section 6.1 is the set of rational numbers. The first thing we're going to talk about is what a rational number is. A rational number is simply a number of the form a over b, i.e. a fraction, right? Where a and b are integers. And we do have to have one more detail that says that b is not 0. Why is that? Well, 0 is a whole number, so that's not a problem. It isn't a counting number. That's not still quite right.
0 can't be on the bottom.
Yeah, the b that we're actually talking about here is referenced over here, and it's on the bottom of a fraction. And we don't have it has 0 on the bottom of a fraction. There's divisible by 0 is what we call undefined. Okay, it doesn't work. We'll talk more about why later. Now, specifically, you see a fraction is defined as any number of the form a over b, where b is not 0. So what's the difference? I mean, those are almost the same definition. What's different?
Rational numbers, integers.
Yeah, it's this part that says integers. Now, you may remember from previous math classes, or you may have forgotten. What's an integer? Do you remember?
Up to anything.
That's part of them. So 0, 1, 2, 3, 4. Those are all integers, and keep going.
Be negative numbers.
And the negatives, right. So your integers are the positive and negative, what we call whole numbers. Okay? So those are integers. So if you have an integer on top and integer on bottom, it is a fraction. It's also a rational number. If you have something that is not able to be written as an integer, like a square root of 2, pi, right? Those are irrational numbers. They're numbers that are not able to be written as a whole number or an integer. That's when you have something that's simply called a fraction. So if you had anything in trig or geometry in high school where you wrote down something like pi over 2, right? That's a fraction, absolutely a fraction, but it's not rational because the pi is not a rational number. It cannot be written in a closed form. Okay? All right, numerator. What's the numerator in this fraction that I have set up here? A. And denominator?
B.
Perfect. All right. There are at least 4 uses of rational numbers that your book brings about. The first use of rational numbers is to be able to solve equations that look like 2x equals 1. Here's the problem. If all we have are whole numbers, or even integers, positives and negative whole numbers, there isn't a whole number that actually solves this. Right? If I plug in the number 0 on the left, 2 times 0 is 0. If I plug in the number 1 on the left, 2 times 1 is 2. And we skipped right over equals 1. That's a problem. Right? There isn't anything between 0 and 1 that's a whole number that would work. However, there's fraction that will. So this is one way of using, or one use of rational numbers, is for to solve equations like this. What would this number be? 1/2, right? Partition is another example of rational numbers. So when you're talking about a partition, you're talking about, for example, if you talk about something like 1/4 of my pay goes to rent. It is a part of, that is partition, a part of something else. 1/4 of my students are boys. That kind of stuff. So you're looking at a portion of something else. There's also ratio. So that's an example of one. I almost gave you the same one. So the student to teacher ratio is 8 to 1. 8 students to 1 teacher. So if we wrote that in a rational number form, that would actually look like 8 over 1. I recognize that simplifies to the whole number 8, but it can be written as 8 over 1 in a ratio form as well. A third option here is to talk about probability. So for example, if you roll a die, so when you roll a die, there is a 1 out of 6 chance you roll a 3. Those are some different places where we see rational numbers used. All right, we're going to do some examples. These are going to look a little bit like what you're going to see in your homework. And some of the things that you'll see me do in this class are going to be a little bit different than I would do in, say, an algebra class or something like that. You notice, obviously, I could have created this slide before I came to class. I could have had all my pictures drawn. I don't have them all drawn because I want you to see that you can do this sort of on the fly as well. It's not difficult to create them on the iPad because you guys get to do a presentation on an iPad later on, right? And a lot of schools are going to where you will be issued an iPad if you teach there. I have a friend who is teaching, I think it's 7th grade math at a school in Moore, and she was issued an iPad the other day, and she doesn't know what she's supposed to do with it. And so I want you to be aware of some of the different things that you have at your disposal to be able to use. So the first thing I'm going to do is I'm going to show you that you can actually use this program to draw boxes. So that's what I'm going to draw first. So we're going to draw a rectangle. And I have the tools on here, and so when it comes time for you to do your presentation, they're not scary, I promise. And so you can create different things. Oops. There we go. All right, I'm going to take my image and I'm going to cut it in half lengthwise, and then I'm going to cut it into some pieces on top that should look equally spaced, and I recognize that they don't. But if you were doing this, of course, you would make them look much better. So this is the first one I'm going to do, and I'm going to choose to shade in, and there is a shading option. This piece right here at the top. Okay? All right, so the question asked is, for each of the following, write a fraction to represent the shaded portion. How much of this image is shaded in? It is 1/6. What is something that you might expect a student to do if you ask them this question? To say 1/4, right? There's 4 pieces. You shaded in one of them. So if you were taking a look at this with a student and you were talking with them about this not being the answer 1/4, you might actually show them, oh, in order to do this, we would actually need to make the boxes all the same size, right? All right. So this is the kind of thing that you're taking a look at. Let's do another one. We're going to do another one with a box. This is a similar kind of an idea to the last one. And we're going to shade in down here. Okay, so how much of this is shaded in? How much? This, no, it isn't actually on this one. It's actually 1/4. How come?
Oh, because you split the top.
Yeah, they're not the same size again, right? But it's not quite as easy to make this argument as the last one because I can't just put in extra lines and actually look at it from that perspective. But what I can do is I can say, but all the boxes still have to be the same size. So I can remake my boxes. We'll use red to show that this box and this box are already the same size, or they would be if you were actually doing it properly and more precisely. But you'd actually have to change the top size of the boxes, right? The original black lines that I drew don't work for this because they were different size boxes in the bottom. So there really are 4 boxes of equal size here, so you get 1/4. All right, so there's nothing actually very special about boxes. They're easy to draw, so that's kind of nice. Let's do another image. We're going to do one that's a circle. So I have a great capability of doing a circle as well here. So we're going to draw a circle. And in my circle, I'm going to divide this up into pieces. Again, I'm trying to make them, that was actually pretty good until I got to the last part. Hey, that's not bad. And we're going to do this. All right, so how much of my boxes are shaded, how much of my image is shaded in? 1/3. How else might a student say that? Close, 2/6, there you go, yeah. They might say 2/6, which is actually just fine. There's nothing wrong with 2/6, except that it can be simplified or reduced. And so we'll talk more about that idea as well. But when you're first talking about it with a student, 2/6 is a very reasonable answer for them to say. They're all the same size. 2 of them are shaded. There's 6 of them total. If you wanted to talk to a student about the fact that there's 1/3, what you'd want to do is you'd want to recreate the image to show them there are actually 3 equal size pieces here, right? And one of the 3 of them is shaded in. So you can talk about it from that perspective. All right, last one. This is a different kind of an image to talk about rational numbers from. All right, so there's a copy-paste feature inside of this app is called Doceri, by the way, and it's a free app.
What is it called?
Doceri, Doceri. All I'm doing is I'm going to create images, and because of the copy-paste, they actually will be really all the same size, which is kind of nice. And so we're going to copy-paste some of these in here. So if you were working on these in your classroom, you'd probably have done what I'm doing right now before you showed up in class, right? You're not going to probably want to, unless you just wanted to create one example or something sort of in the middle of class. You're probably going to create something before you get to class. All right. How many do I need? All right. So I've got all these little circles, and we're going to shade some of them in. All right, so how much of this image is shaded in? How much? 7/12, right? This is a very different kind of an image than the other ones. What's different about this last one than those other ones? It's not a whole thing, right? All of those other images were sort of a piece of a whole picture. Now I'm looking at something that doesn't look like a piece of a whole. It looks like just a bunch of pieces. So you might imagine using coins to do an example like this if you wanted a concrete example with children, right? You give them a bunch of coins and two different types of coins, pennies and quarters or something like that. And so they could actually use physical objects where it's not part of a whole to talk about that. All right, some historical thoughts or some historical features. Fractions have been used for a very, very long time. Egyptians used fractions. Their fractions that they used had numerators of 1, which means that they would have never written 7/12 like we had in our last example. Instead of writing 7/12, they would have written it as 1/4 plus 1/3. There's some nice kind of feel to that. All the numerators are 1. That's kind of nice. But I'm not particularly excited about the fact that I have 1/4 plus 1/3 and talking about adding those together in sort of a visual way. It's not very friendly. The Greeks, they adopted fractions with denominators of 60. So now all their denominators are the same. And they did it from the Babylonians, and they still presently use this in measurement of angles. Do you remember doing anything in geometry or trigonometry with 60s? Things with 60 degrees, things like that. We also use it somewhere else. Do you know where we use something with 60s? Minutes on a clock, right? 5 out of 60 minutes in an hour, that sort of thing. So we use that idea of a base 60 a lot. And then the Hindus actually developed our modern bar between the numerator and the denominator. And so that's actually this one, right? So we put our numerator on top, our denominator on bottom. And that's came into use in Europe in the 1500s. All right. There's some different models for fractions or rational numbers that you should be aware of. There's an area model, which we've actually already used because I drew two area pictures. And so you have images there where they look like a rectangle. And then we divide them into pieces. And if you had, for example, the number 3, all right, try again. Three over 4. Then in your image, you could actually take that and you could shade in 3 of the 4 boxes. So that's an area model. This one we haven't seen yet, the number line model. I didn't do an example of this one. But if we're using that same example of 3/4 and you're doing a number line model, You would have the image of starting at the number 0, and the sort of ending place is the number 1, and dividing the mounts between it. So this one's really nice to do it in half, and then in half again, and so my number is 3/4 right here. So this idea of number line is used a lot when we talk about distances. So we see that used. Or even just values between other values. This is a new concept. You can't do this with whole numbers. There is no number between 0 and 1, right? Not in whole numbers. But once you get to rational numbers, you can always do it. And we'll talk more about that later. Set models, where we've actually did this one as well, just a minute ago, had the feature where I did my coins, if you will. Right? So I have these little circles. And there's nothing special about a circle. You could use little squares or something like that too, and that would be fine. But if we are going to do this with my number 3/4, whoops, I did it again. So you have 4 objects and you shade in 3 of them, would be the number 3/4. And that works fine if you have 4 objects and you shade in 3 of them. The problem with this when it says note set model has limitations is, what if you accidentally gave the kid 5/4? What's 3/5 or what is 3/4 of 5? It doesn't work very well. So you have to be very careful when you're using this set model to talk about ratios that the denominator really makes sense with the coins you've got or whatever counters it is you're using. So it has some limitations when you're thinking about this particular form of the model. All right. Theorem 6.1 actually talks about when fractions are equal. So Shayna, you mentioned 1/3 and 2/6 a minute ago when we saw that image. This is where we're going to talk about that. So if we have a value a over b and it's a fraction, and we have any other value n that's not 0, and they're using it to be an integer, although this theorem holds true whether it's an integer or not. But it can't be 0. That's important. Then if you actually take that a over b and you multiply the value on top and the value on bottom, the fraction is what we call an equivalent fraction. It makes the value the same. So when we looked at the number 1/3 and the number 2/6, it was the same. And looking at it from the perspective of the way this theorem is written, the reason that's true is because if I take the number 1/3 and I multiply it on top by 2 and on the bottom by 2, I would get 2/6 and it's the same value. So that's the theorem's sort of whole point, is that you're able to do that. Now you usually see that done, well you do see it done in this direction, what I just did here for some reasons, but you usually see it talked about in the other direction as well. This idea of creating something and make it in simplest form. In fact, I think some of you use that phrase simplest, others of you use the phrase reduced when we were looking at this number 2/6 and 1/3. And so if we take the rational number a over b, we call it simplest form if the numerator, a, and the denominator, b, don't have anything that they can both be divided by evenly. So what we say is their GCD, this stands for greatest common divisor, is 1. That is, you can't divide them both by the same number and still end up with whole numbers. You can always divide them by 1, because that doesn't change anything. But it's in simplest form if you cannot divide it by anything else. So the first example that we're actually going to do, like real life example, is we're going to take the fraction that's given here, which is 3/-14, and we're going to write 3 additional fractions that are equal to this one. So somebody give me an example. What is another fraction that is equal to 3/-14?
6/-28.
Perfect. 6/-28. And we get that by doing what?
Multiplying it times 2.
Yeah, multiplying top and bottom times 2. Somebody give me a different one. -3/14. Shayna, what happened? Yeah, it sort of looks weird. It doesn't really look like it's a different value because we don't think of it as being a different value. But, I mean, like, reality is, guys, none of these are different values. These are all the same value, right? Every example we're going to write down is the same value. So it sort of looks funny. It looks like I just moved the negative to the top. But Shayna's exactly right. What we really did is we multiplied the top and the bottom by -1. That's an integer. That's fine. Let's do one more. Somebody give me one.
12/56.
All right, -12/56. What did you multiply by, Shayna? All right, and actually -4, right? Yeah. All right, so this is an example where your answers may not even match somebody else's, and that's okay, right? There's lots of these, infinitely many different examples you could write down. There's plenty of things you could write down that are wrong. I don't want you to think that anything you wrote down would be right, but there's lots of things you could write down here that would be right. All right, example 2 actually gives us a fraction and asks us to take this and turn it into simplest form. I bring this one up specifically because what I don't want you to think you can do is to take those little squares and just mark them out, because you cannot do that, okay? We can't just nix off the little squaring business. That's inappropriate. And I'll show you why as we do the problem right and how that would actually fail you if you had tried to do that. What we do want to do is we do want to look at the 42 and the 35 and ask ourselves, what are they both divisible by? That is, how can I write 42 differently and 35 differently in a simpler form? There is a 7 in both of them. So the 42 can actually be written as 7 times 6, right? So for now, let me just write it like this. And how about the denominator? 7 times 5, exactly. Now, we haven't done it yet, although we will very soon, I think. I think it's this lesson. Talk about this idea of these squares. But what squaring means is multiplying something by itself, right? So if I have 42 squared, it really means I've got 42 times 42. And if I have 35 squared, it means I have 35 times 35. So what that means is that I don't have 7 times 6 squared. I could write it how else? Exactly. 7 times 6 times 7 times 6. And do the same thing in the denominator, 7 times 5 times 7 times 5. And once it's written like this, you see things that actually match that you can simplify, you can reduce. It's all multiplication, right? Now, we said just a minute ago that 1/3 and 2/6 were the same because you can multiply across the top and the bottom by the same number. Agreed? Well, you can do it with division too. You can divide across the top and divide across the bottom. So the equivalent thing is when I mark these 7s out, what I'm really doing is I'm dividing both the numerator and the denominator by 7. Or you could say I'm multiplying by 1/7. But I'm reducing both of them because it's all multiplication. And multiplication and division are actually the same thing. I know that sounds sort of strange, but they are the same thing because multiplying by 7 would be the same thing as dividing by 1/7 and vice versa. But I could do that twice, right? I can do that with the other 7s as well. And then my final answer down here then would be what? Well, can we do that with the 6s or the 5s? No, I mean, we could write the 6s as 3 times 2, but that still doesn't really help us, right? Because they're not going to turn into 5s no matter what I do appropriately. Well, I mean, like if I do things inappropriately, they could. But that's not the goal. So we can't do any division or multiplication and turn those into 5s. So there's nothing else I can do, which gives me a final answer of what? Right. Now here's the problem. If we had simply canceled the squareds out, which is a common mistake, we would have ended up with only 142 on top and only 135 on bottom, right? Which means we would have written the 42 is 7 times 6 and the 7 times 5 and 35. We wouldn't have this piece here. And the answer would have been 6/5, which is not the same as 36/25, right? So we can't treat a squaring process like we treat a multiplication process because squaring doesn't multiply it by the same value. It multiplies it by itself, which may or may not be the same value. All right, Theorem 6.2. Theorem 6.2 says that A over B and C over D are equal if and only if AD equals BC. And sometimes people will call this what? Do you remember? Yeah, they'll talk about this being cross multiplication. So we're saying something like this. A over B equals C over D. If when you circle these here and you multiply them, they equal the other diagonal multiplied. Okay. So this is one way. There are more than one way. I'm about to show you several ways. But this is one way to determine if a fraction is equal to another fraction, is to do this cross multiplication of numerators and denominators. So this question right here, and it may not be the easiest way, If the values were very large, you might not want, and you didn't have a calculator, you might not want to cross multiply. It might not prove to be the very most helpful thing. These particular values are not especially friendly, but they aren't horrid. So we're going to do this 4 different ways. We're going to show whether these fractions are the same. So the first way we're going to do is simply Theorem 6.1 because it's the first one we just mentioned. So this is my first attempt at deciding if these two fractions are the same. Let me just say real quick, a non-valid attempt is to use your calculator and turn them into decimals. The reason that's not valid is because we have not talked about decimals yet. That's the next chapter. So while you can definitely confirm to yourself the validity of your answer, that is, are you right or wrong, it's not an acceptable reason of why you're actually correct. Does that make sense? Decimals are actually based on the fraction work that we're going to be doing. So turning things into decimals right now is not an appropriate response to this question. All right, however, it is appropriate for us to use Theorem 6.2, to take that negative 3 over 12 and this negative 36 over 144. You can put the negatives. In fact, to be honest, you could ignore the negatives because they both are negative, right? So that's not going to change anything. So we could virtually ignore the negatives for the moment. It didn't matter. We're just dealing with whether the values are going to be the same in terms of the numerical value. So we need to know what is 3 times 144, and then what is 12 times 36. So what do we get? And you're welcome to use your calculator to do the multiplication. What do we have? 432. And they're both the same, right? They're technically negative 432s because they were both negative to start with, but are the fractions equal? Yes, they are. So yes, they're equal. So this is telling us that, in fact, negative 3 over 12 really does equal negative 36 over 144. This is a true statement. They are equal. All right, we're going to do option number 2, or method number 2. One way to do this would be to take fractions, especially if fractions are not simplified, and to simplify both of them. So we could simplify them and compare. So if I take negative 3 over 12, 3 and 12 have something in common. What do they have in common? 3, and then I'll get a 4, right? So if I divide them both by 3, this actually ends up giving me the fraction. Yep, and it's negative still, so negative 1/4. I can actually do the same thing with the negative 36 over 144. Now, from the last problem, the last part of this problem that we already did, you probably should know that they actually divide by 36. You probably wouldn't know that just looking at the numbers from the very get-go. However, you might look at that and say, I know something does divide them. What do you know divides 36 and 144 legitimately without cheating, so to say? 12. They're both divisible by 12, so that might be a good place to start. So if I divide them both by 12, 36 divided by 12 is?
3.
Yes. And 144 divided by 12? 12. Now, you could actually stop here if you want because you're to the point where you got where the other one was. You know, this is also going to become 1/4. Okay, so simplifying and comparing is another very viable choice, especially if you already know what they simplify to or can see something that simplifies very quickly. Third option, we're going to find the LCD. Do you remember what LCD is? Least common or lowest common denominator. Yes. Just a moment. Okay, so for these, the lowest common denominator is actually 144. Because if you take a look at the 12 and the 144, you probably recognize that 144, just like you did a minute ago, is divisible by 12, which means that if you take the 12 that's already there in the 3 over 12 and you multiply it by 12, you would get the 144 that's already in the other one. And then if you multiply that negative 3 times the 12, you get the negative 36, which is exactly what the other one was. Right? They are equal from that perspective. So you can get a least common denominator. Sometimes finding a least common denominator is not very easy. If you were to take the numbers, say, 24 and 40, it's actually kind of messy to find that. You have to factor them, and then you have to see what they have in common and see what they don't have in common, and you have to multiply some things together. So piecing all that together, it might actually be more work than this last one. So the fourth option is finding a common denominator. Any common denominator will work. The simplest way to find a common denominator for any fractions, I agree that this is not going to be practical on these particular two fractions, but the simplest way to find any common denominator is simply to multiply the two denominators you have together. Now, this is going to be a big number on this one, so that's why I say it's not especially useful on this particular problem. But if you had 40 and you had 24, I can multiply those together fairly quickly. And I don't have to factor anything or look for anything in common. I just multiply them. So this one, we would actually take the negative 3 over 12, and we would multiply it by 144. And we would take the negative 36 over 144, and we would multiply it by 12. So what is 12 times 144? Anybody? What'd you get? It's a big number. All right, I'm going to spoil the fun. I think it's 1728. Does that look right?
Yes.
Excellent. Somebody tell me what the fun is on top. What's 3 times 144? 438?
No, 432.
432. No problem. And it's negative. Just all of them have been negative. And so once we got the common denominator, the fractions end up matching as well. Okay. There's really not a right or a wrong method here. There's nothing special about method 4 versus method number 1. It really depends a lot on what the problem is you're working on. However, what's really important for you as future teachers to understand is that method number 1 doesn't really look like the fractions are the same. It looks a little bit like magic. Do you see that? I don't know, and maybe some of you feel this way too. Sometimes people really think that people invented math. I promise you they didn't. It's not like that, all right? And so it's very good when you have a method to do something to know another method, because some student is going to challenge you and say, but why? Or I don't understand that method. They may not even be challenging you. It may be a legitimate, I don't get it. And if you have a secondary method, a different way to show them, it may make a lot more sense to them than the first way you did. So just because it's a method you like doesn't mean that it's necessarily a method that your students are going to like. So having more than one method, and that's the theme. It's the whole theme of elementary math 1 and 2 and 3 is having multiple methods to do different ways, different methods. I'm not saying that very well. Multiple methods of doing different mathematical problems, okay? Because you don't know how your students think until you actually start working those problems with them.